Hey, welcome back to Parametric Equations in Calculus, and this is the final one in the very theoretical approach to parameters and calculus, but the final one is an interesting practical application, so you have to wait for that one. Let's have a look at what we're doing here, and I've got a question for you. Always have a question in maths, eh? And so here it is. Did you realise, there you are, did you realise the following? And what's all around the screen? Well, what's around the screen is a reflection upon what we've been doing so far. Parametric equations is quite a theme in this course, and it's important to pick that up. So recently we've been looking at this, the unit circle, and how x and y can be written in terms of cos t and sin t from the last presentation there. And then, of course, do you remember back to vectors? There we have the vector equation and the parametric equations using the parameter, what? The parameter t. Did t mean time here? No. Look at it. Look at what's happening. It was a number of lots of the direction vector to create points or to travel to points out along a particular line. You remember that? And what about this sort of stuff? Again from vectors, and where we're trying to solve 3x3 systems where they mean the coordinates of points in 3D space. And this one, of course, has infinite solutions. And we use parametric equations, a free parameter if you like, t, where t could be any number in the real number set, to describe the infinite number of points that were the solution of this. So that was a line of solutions, wasn't it? And then, of course, we recently had Bezier, where we have t again meaning something different. Do you remember what that meant in Bezier curves? T was the ratio of division, t and 1 take t. Okay, do you remember that? So we've done quite a bit of work with parametric equations in different contexts. And what this presentation is about is working with them both per se, by themselves, and in conjunction with the Cartesian form. Okay, so let's go down and have a look at what we're doing here. So the first question we want to say is, if we have parametric equations, how do you connect back with Cartesian form? So that's what this little section's about, and a little bit more too. How do you do it? How do you work backwards from parametric equations to Cartesian form? Let's see if you can remember it. So what was the idea here? The idea was to isolate t from each one. So here we could say, hang on, I'll do this differently. I'll do it as it stands here. X take x1 equals at. Divide both sides by a. X take x1 over a equals t. And then we did it with this one. Do you remember this back in vector land? Y take y1 equals bt. These are the parametric equations of a line using a vector approach. And this one, do the same thing. Watch it carefully. Z take Z1 equals CT. So Z take Z1 over C equals T. And then we said all the meaning of T, the parameter T, is the same in each one. It's the multiples, if you like, of the direction vector to get to a point. So in each context, these are all equal. And so the Cartesian form, parameter free, just in X and Y land, X, Y and Z land, sorry, it looks like this. You remember that? So you must be able to do that. And also, remembering here, these are the components of the direction vector, aren't they? I hope you remember some of that stuff. So what have we actually done in this process? What we've done is gain an expression for t from each of the parametric equations, expressions for t, and equate them. Okay, so you've eliminated the parameter, and now you're going to work with just a Cartesian form. So that's the first thing we want to do, is relate it back, connecting back with Cartesian form. Okay, what's the other thing we want to do? Come down here, and the next question is this. Is it always possible? So what have I got here? I think you'll recognise these as equations describing Bezier curves, where t and 1 take t are the ratio of division of the line segment. You remember that? Now, do you think it is possible to get a Cartesian form from this? Okay, pause the presentation and just have a discussion about that. Okay, so coming back, is it possible? Well, you can't actually get an explicit statement in t here, okay, because you've got t cubed, t squared, t. Oh, so that's not going to be possible, is it? So you won't be able to get a Cartesian form connecting x of t and y of t easily here. Okay, so that'll fall down. And I suppose that's one of the reasons why the Bezier curves sort of work, don't they? Because you've got x dancing to, if you like, to one tune or polynomial in t, and you've got y, the y coordinate point, dancing to another one. So that's how we're going to generate quite complex curves. Okay, you might go back and review that. So it's not always possible. What else would we like to consider? Well, here's a good question, and you already know the answers, but you might not realise you know the answer. Can both systems work together? What systems am I talking about? I'm talking about the systems of describing lines, curves in Cartesian form versus parametric form. Can you work together? Here's a question from back in vectors, 3D vectors. There's a line in vector form, and here's another one in vector form, or parametric form, sorry. And here's a line in Cartesian form. Do you remember this example from Hayes and Harris publications there? Check it in your textbook. Show that line 1 and 2 are parallel. We won't do that. Show that line 2 and 3 intersect and find the angle between them. So this is the one I'm referring to. Right? You can actually use line 2 and 3, line 2, parametric form, line 3 in Cartesian form, and join the two together. Here we are. They're going to intersect when what? When the conditions from line 2 satisfy the conditions from line 3. So where's line 3? So we'll take this and we'll say if it intersects with line 2, you can replace x by, there it is here, x by 1 take t, and y also by 1 take t, and that's been done there, it's not so obvious. And here's the z. Let's just go up the top here a little, because this is what we're doing. See the z? If we're talking about intersecting with this line, we're going to put that z parametric form from one equation in place of z in the other. So this is finding their common point, putting the two equations equal. Only we're going to do it in pieces. Okay, so we're going to put the x and the y and the z in place of, in t's, in place of those variables in the other equation. So you can have a go-between. You can work with both systems. And what do you notice now? So if you replace it all with t, you find and you check with both this equation, producer t, this pair of equations, producer t, and you check that they're the same. So you do find that there is a solution when t equals -2. And this, once you specify the value of that parameter t, you lock down a point, don't you? That's a little bit of Huddyism there. You lock down a particular point. Okay. So when you say t is -2, go back in here and you'll be specifying an actual point on that line, and therefore on the other line as well, their common point. And that's what the substitution is down here now, and you've actually found the common point. Okay, I'm not going to do the rest of that problem. That's been done before, earlier presentation from the textbook there. So you can work and go between the two systems. But the idea, of course, is just like that. You're going to substitute the parameter, the parametric form, into the Cartesian form, the parametric form. Okay, and that's going to give rise to a t value and a solution, quite possibly in this sort of context. let's go down and see what you can do. Let's have a look now at an example from Hayes and Harris Publications. Okay, find the Cartesian equation. So this is the first idea of this presentation, to try to go from parametric form to Cartesian form. So here we are, here we have the first pair. So you will isolate t, they've done it differently. So here we've isolated t from here, t is 1 take x, and substituted it in place of t there. There it is there. Or you could get two expressions in t. Let's do it that way. So t is 1 take x from the first one, and taking it from here, y take 3 on 2 equals t, and then put those two equal, getting a go-between, if you like, of t, going between the two parametric equations. 2 take 2x equals y take 3, so it would be neg 2x plus 5 is y. So it's the same expression as this one here. So you can do that, take an expression of t, substitute in the other parametric equation in place of t, another way of doing it. And that's what they've done here again. So they're taking this one, getting a t expression and putting it in place of t in that one. Now that's not a bad trick here, because it's not easy to rearrange this to get an expression in t, is it? Because of t squared take 2. You've got two different powers of t, so an explicit statement in t, for t in terms of y, is not going to be straightforward. You can't do it. And so we will use this substitution method. All right, so think of those approaches. So I'm wanting you to have a look now at doing some. So here's 6E1, sorry, and you need to do all of these. If you want to have skills to perform in tests and exams, you need to do the practice. It's like, are you a soccer player, maybe a basketball player? No good going out and watching the coach, and here I'm coaching you, mate. I'm watching the coach shoot baskets or pass the ball. You've got to do your work on that, your lap running, if you like. You've got to do your practice. And so it is with maths. You're not going to be good at it unless you go away and practice it after you look at the coaching session. Okay, pause the presentation, have a go, and I'll ask you to have a look at the solutions now. Okay, so here are the solutions. So showing you exactly how to do it. So study those. Okay. And we'll just go down the bottom here. Last one there. Okay. Let's go on and do a little bit more. So here's another example, this time working between the two systems. Here we have a parametric form for a line and meeting a circle in Cartesian form. So what will we do? Sorry about that. What we'll do, we'll take x is t and y is 2 take t and substitute them in here. We get a quadratic in t, simplifying it, just work through that. Remember here, perfect square, first one squared, twice the product, which is negative 2t, twice is negative 4t, and second one squared. We get this and we can factorise it, or use the formula for the roots of a quadratic. You should be able to factorise it, but you've got this, or you've got your calculator, but they might ask you to show the algebra. Okay, so you've got t is 3, or neg 1, so it looks like it intersects at 2 points. When t is 3, stick it back up in this pair. So t is 3, we've got 3, and 2 take 3, neg 1. So this is the generator of the points here on that line. And then at neg 1, subbing it in, you get t is neg 1, get neg 1, 3. Okay, so explaining there, those 2 points are generated by those two different t values. Remember, once you specify a t, it locks down a point. You stop the growth of that line, if you like, and you produce a single solution. So what's happening here? Well, I don't know. Can you have a look at it? Let's just do a little bit of business here. X squared plus y squared equals 10. There's a circle around the origin, with a radius of root 10. I don't know whether you know that from our earlier work. X squared plus y squared equals 1 was a unit circle, so this would have a radius of root 10 now. All right, so it's been enlarged. And what about x equals t, y equals 2 take t? What is that? That's y equals 2 take x, or y equals neg x plus 2. So now root 10 is about 3, so 2 is there somewhere, and neg x, okay, so neg x runs through here. So we're talking about these 2 points, 3 neg 1 and neg 1 3. Oh, this is about right. It's a little bit cockeyed. So that's these 2 points here. So try to picture what's going on, because if you can get up close and personal with maths, it's fun, isn't it? Okay, so let's go on now. You don't need this, of course, but that's just for your own interest. Say, hey, what's going on in this question? And this is what's going on. And you're doing it algebraically. How nice is that? All right, let's get you to do some now. So here's question 2. And question 2 is about combining the 2 systems and seeing if we can get points of intersection and so on. All right, let's have a look at, have a go, and let's have a look at the solutions now. So that should be good. All right, moving on, let's have a look at tangents and normals again. This is quite important in this course and will be built upon later on when we look at motion as the last topic in actual fact. So tangents and normals, just remember this result. This is to do with the chain rule. So that's where this came from. The idea that the slope of the tangent to a curve is the derivative of y with respect to t divided by dx with respect to t. And so it's y dashed over x dash. And just remembering now, that's the velocity of the point travelling around the curve, and the slope of that velocity function will be equal to the slope of the tangent, so it'll be tangential. Okay, we discussed that earlier. Okay, so let's get rid of that. Let's go on and see what we can do with that. All right, so here we are, finding tangents and stuff. So find the equation of the tangent of the curve with parametric equations, this and this at t equals 2. So there is a process, isn't there, for doing this. You first of all probably want to find the slope of the tangent. What's its slope? Because if you're finding an equation of a line in Cartesian form, you want its slope and you want some point on it, don't you? All right, so let's have a look at that. So let's find its slope. Slope is dy by dx, but you haven't got a y expression explicitly in terms of x, so we'll use dx by dt and dy by dt. So we're going to differentiate this and get 2, differentiate this and get 2t. Okay, so dy by dx is 2t over 2, which is t. When t is 2, because we're given that particular point, dy by dx is 2. And also we can put, they haven't shown that here, if we put 2 back in these equations, we find that x is 7 and y is 4. So now we have both of the things that we want. We have slope and a point on it. Just remembering, when you see this t is 2, you know you're going to be locked into a particular point, and you should find that point by substituting into the parametric equations. So what have we got now? This is the preferred way of writing the equation of a line. Y take the y coordinate of a known point on the line, so that's that, over x take the x coordinate of a known point on the line equals the slope. So what we're doing there is delta y on delta x, or y step on x step, and taking it that we know a point here, so this is a point 7, 4. What would the general rule be for a point further out? It would be y take 4, which would be the y step, over the x step, x take 7, has to always come to the slope. That's what we're saying there. This is preferable to y equals mx plus c. Okay, so it's a bit neater, particularly when you get fractional values for slopes. Okay, so multiplying both sides by x takes 7, and then getting all terms crossed to the right, adding that 4, you get the equation. Okay, so it's fairly basic stuff. You must remember what's required for a line though. You need a slope and a point. Okay, your turn. Come down and have a look at 6E2, question 1 and 2. So it's the same sort of thing. Please remember the result. The slope of the tangent to a curve is dy by dt over dx by dt coming from the chain rule. Okay, pause the presentation. Have a go at both of those. I'll go and show you the solutions now. Okay, so here are the solutions. Just check it out. Very, very important that you get your head around this. We're going to be using this again later on. As I said, it's a thread running through the course. All right, what else can we do? Well, there's a little bit more here with calculus. Let's have a look at this one. Find the equation of the tangent to the curve with parametric equations that and having a slope of a half. So, find the equation of the tangent, equation, I'll need a slope. So let's get dy by dx by t and dy by t. Differentiating this using the x to the n rule, 2t, derivative of this is 1, so the slope is 1 over 2t. Remember, it's dy by dt over dx by dt. Okay. And the slope has to equal a half. So we've got to use that. Use all the given information. Notice here you're not directly given a point on the tangent. You're not given a t value to sub in to get a point. So you can use the slope being a half to specify, we've specified a t. When you specify a t in parametric land, you are locking down a point, aren't you? Locking in a point. Okay, so now we have, if we take t is 1, we can put it in up here and we get the point 1, neg 1. And so the tangent is y take a y, the y coordinate point on line, over x take the x coordinate, and that has to equal a half. So this is a bit of a tricky-dicky way of finding the point. Please remember, when they say equation of a tangent or straight line, you should be thinking, I need the slope or gradient and I need a point on it. So know your work, and then that helps you, so know about your work like that. And then that helps you realise, this is what's missing, and I have to seek out a value of t to lock in that point. All right, your turn, and that's the end. So let's have a look at a few questions here, 3, 4 and 5. Now these are important because down here particularly, we're getting on to questions where they aren't straight, typical questions. You have to do a bit of thinking and extend it to situations which are a bit more general. Okay, so I want you particularly to focus on those two, but you should be doing all these questions if you want good performance in tests and exams. Okay, pause it, have a go, and I'll go forward to the solutions now. That's question 3, A and B, and C. Question 4 and question 5. We haven't got all of it. I'll keep going. Question 5 is a big one. Make sure you can understand and do question 5. Get a clue and go back and try it again if you weren't sure. All right, well, look, we finish up there for parametrics at this stage. The next presentation is very interesting. It shows you a very practical use of parametric equations, and particularly where the parameter is time. Okay, so I'll catch you then. Cheers for now.